Okay, so just recapping. So I've got this lambda is an eigenvalue of the square matrix A if and only if this, I put the I in this time, right, has a non-trivial solution. So AX equal lambda X or A minus lambda IX equals 0 has a non-trivial solution. That means is a free variable. Okay, so look at that. I've got it equal to 0. Ooh, if I've got something equal to 0, talking about the homogeneous equation, doesn't that mean I'm talking about the null space of this matrix A minus lambda I? And so we're not going to call it the null space because we're talking about eigenvalues, so we're going to call it the eigenspace. So it's the eigenspace of the matrix A corresponding to that lambda. Okay, here we go. So find a basis, which just means find the vectors that, from the free variables, from the non-trivial solution, right? Find the basis for the eigenspace for this lambda and for this matrix A. All right, so first I'm going to go find A minus 4i, right? A minus 4i, and I get this. So this A minus 4i is this matrix here, x equals 0. So I put it in augmented with 0, and I get this. So what does this mean? This means x1 is equal to 3 halves x2, and then x2 is a free variable, right? So my vector x1, x2, right, is 3 halves x2, x2, factor out the x2, so hopefully you're comfortable with this, right? So x2, all right. So this is a basis for my eigenspace. So what does a basis mean? It means any linear combination of this one vector spans all the solutions, right? Well, since we're talking about linear combinations that span the solution set, I could take this vector and multiply it by 2 and get this vector and say the basis is this. And we usually like to have the ones without the fractions, so you can get comfortable with that. Remember, you could only change a vector if you're talking about it being a basis or a vector that spans a solution set. All right, let's go do another one. So here is my matrix. So find a basis for the eigenspace for this matrix corresponding to this eigenvalue of 3. So again, I'm going to want to find A minus 3i. So 3, 0, 2, 1, subtract 3, right? So this matrix here will give me, oh my goodness, 0, 0, 2, negative 2. All right, so to solve this, so make sure you're kind of showing what you're doing, right? So what I'm doing is I'm solving this, and I'm pretty sure I can do this without a calculator. Switch the rows, divide through by 2, right? I get to this. Okay, so what does this mean? So this gives me 1, negative 1, 0, 0, 0, 0, right? When I augment it. So this first row says x1 minus x2 is 0. So x1 is x2. So my vector x, x1, x2 is x2, x2. So that must mean if I factor out the x2, there's my eigenvector. So my basis, basis for my eigenspace will be that one vector, 1, 1. And this means the span, right? These little parentheses. So this is the basis for the eigenspace for lambda equals 3. All right, so let's get to a bigger guy here. My lambda this time is a negative 5. So AX equal negative 5x. So that's going to be a plus 5i, x equals 0. Right, don't go too fast through steps because you could make mistakes, right? So if I take a plus 5i, so this plus 5i, I get 1, 1, 1, 2, 2, 2, oh my goodness, 3, 3, 3, x equals 0. Okay, so again, I can do this without thinking about it, right? Multiply this row by negative 2, multiply this row by negative 3, and add. So what I end up getting from my augmented matrix with 0 is this. So this says x1 plus x2 plus x3 equals 0. All right, so x1, 2, and 3. So negative x2 minus x3, x2, x3. So factor out an x2 and factor out an x3. And there we have it. So my basis will be these two vectors, negative 1, 0, 1, like these. Okay. So let's talk about this. Hold on, I'm going to go back to this thing. Every eigenvalue has at least one eigenvector. So this eigenvalue of negative 5 gave me 2 eigenvalues. That was at least one, right? This eigenvalue of 3 gave me 1 eigenvector, right? So every eigenvalue has at least one eigenvector, right? If there exists one. Okay, it can have 2. So if it has more, right, like 2, this one here has 2 free variables, so it gives you 2 eigenvectors, and these 2 eigenvectors are linearly independent, right? If I put these together in a matrix, I could see that I have a pivot in every column. So these two, so when one eigenvalue produces more than one eigenvector, they will be linearly independent. All right, so another kind of question. So what does it mean to have an eigenvalue of 0? So that would mean ax equals 0x, right? So that means ax would equal 0. So if 0 is an eigenvalue, that this means this has a non-trivial solution. So if this is a non-trivial solution, that means that A is not invertible. There's not a pivot in every row and every column. So bottom line is, if A is not invertible, that means lambda equals 0 is an eigenvalue. So here's a little theorem, made a comment below it. So if I have r different eigenvectors that correspond to r different eigenvalues for some n by n matrix, then those eigenvalues will be independent. So be careful. So this is saying that for each eigenvector, there is an eigenvalue, right? For these r eigenvectors that correspond to distinct eigenvalues. So that means every eigenvector and every eigenvalue, there's only one. So it is not talking about this situation right here, right? So just a theorem there. We'll come back to different things like that. Okay.